Hello there everyone, and welcome to another TouchDesigner tutorial. In this tutorial I'm going to do a sort of improvisational show and tell where I jump into the neighbor pop. Now I haven't done a standalone video on the neighbor pop before, but I have used it in examples like this where I'm using the neighbor pop to get neighboring particles and creating a sort of boundary so that things don't overlap too much and push away. Now in today's tutorial I'm going to dive into the neighbor pop, show you its basic operation, as well as a few things that I had overlooked until recently that I think are really cool effects. Let's begin. Starting in a blank project, let's make a point generator so we have some kind of input. I'll move the number of points down to 1000 and let's bring that into a neighbor pop. Now in the neighbor pop we have a few options here. First off we have the neighbor's type, which I'll keep as by distance. We have the max neighbor's distance, which we can think of as sort of a threshold. We have the distribution, where we can control the type of neighbor distribution algorithm that we're using. We have these hash buckets, which we'll leave for now. We also have the output options. So for this is one of the things that I had overlooked. Before I'd previously just output neighbors, but you can also output average and inverse weighted average for distance, which are both really useful, and I'm going to talk a bit more about that later. We also have max neighbors, so this is how many neighbors you're going to have as your maximum value to check for. And you can toggle on the neighbors and num neighbor parameters, as well as distance, where you can output the distance between different neighbors. You also have this ability to output different neighbor point attributes, and again we'll look at that a bit more later. If I bring this out into a dat pop2, and let's view that nice and big, what we can see is we have our index and point values. We also have our distance values, which we've just added in. And then we have our neighbors. So this is the 4 closest neighbors. And then we also have the number of neighbors. So this basically tells us for point 0, we have 2 neighbors. And for point 4, we have 4 neighbors, etc. And you can go down and see how many neighbors are present here. Let's select just distance, neighbor, and num neighbors so we can just view this a little better. And what we can see if I tweak some of these values is these start changing. So if I move up this max neighbors distance, we can see that we immediately get lots of neighbors, and this is because basically everything is sort of in proximity to all the other points. So of course we have lots of neighbors, and we're limited at 5. And what we can see here as well is we have all these parameters we've selected. We have 5 outputs. We can think of this as like an array. So our neighbor array is giving us neighbor 0, 1, 2, 3, and 4. And apologies, earlier I said for neighbors that this value was the position, but it's actually the index that you can then reference to find that specific point. So what we can see as well is that whilst we have all this data, the neighbor pop doesn't actually do anything in terms of effects. Let's bring this into something and play around. For starters, I'll just use a delete. Under attribute, I'm going to look at my distance, and then I'm going to move this slider just so we can see as I start moving up, our neighbors get deleted. And we can flip this around and have the other option. It might be clearer if I make my point generator a lot more dense. And what we can sort of see is that neighbors that are very close together are getting removed before neighbors that are sort of further apart. So it allows us to kind of sense that proximity there. Something else we can do is to put a second source into our neighbor to act as a second input. So let's add in another point generator. We'll make this just 100 points, and I'm going to plug this into my neighbor. Now, rather than looking at each of these points in proximity to each other, the neighbor pop looks at all of the points in proximity to this input. So think of this as sort of a controlling field. If I move this down, we can see that this is more or less going to correlate with these point positions. And if I move this with some noise, and animate it. And I'm going to turn up the amplitude there. What we can see is that is moving around in that field, allowing us to delete particles that are close to those points. I'm going to pull this into a null, make the viewer active, and look at this as geometry. So now we can see this a little bit better. Now, what I want to do next is I want to try some of these different output options. The next output I want to try is average. And what we'll see is that distance array that we were feeding into the delete has now gone. I'm just going to disable this for now. And under neighbor point attributes, I'm going to select P. And now what we can see is we have this output that is controlled by proximity to these input points. And then we can get an interesting sort of diffuse plexus effect. Let's take this one step further and look at the inverse distance weighted average, and that becomes slightly more cohesive and coherent as well. And I think this is a really cool effect to get that sort of warpy plexus effect from a bunch of points without actually having to use the proximity pop. So this can be a really interesting technique to add texture into your networks. Let's play with the value a bit. We can make things that are a bit closer to the original form, or things that are much more diffuse and pulled towards these lines. We can also play with these max numbers for weighted average. As we move down, the system will become a bit faster, and this really means we're doing less checks between these max neighbors. Let's set it up to like 10. And as we get higher, we can see that the uniform quality of that shape is less good. So if we have a smaller value, we get this more diffuse network, which I think is pretty cool. I'll put that up to 20. So this is something that is a really cool effect. And I'm just going to go ahead and delete this delete for the next example I'm going to show you. And what I want to do next is I want to toggle on this add prefix. And what this does is it allows us to keep our regular P whilst also creating a cloned attribute. So we have our regular P and we also have our neighbor P. And let's just look what happens if I replace that using a math mix. So if I say A neighbor P is P, then we get that effect. And what this means is we can have our original points whilst also having a separate copy of this inverse weighted average, or the average. And this can be really useful for a number of things. What I'm going to do here is I'm going to take a direction from each of those particles and make it pull towards them. And to do that, I'm going to use a minus B. I'll keep my scope A as neighbor P, and I'm going to do minus P. And let's call this dir for direction. What I want to do is I want to multiply that direction by a very small value to scale it down a bit. So I'm going to say dir times 0.05. And then I'm going to add it to my P attribute. So A plus B. So P plus dir. And right now you won't see very much happening. But what I'm going to do here is I'm going to add in a feedback before my neighbor, and I'm going to drag my null into that. And so now we can see that we have created this sort of attraction network that's pulling towards these input points that we have set up. If I change this value here as well, we'll see that there's a bit of movement there. I'll add a keyboard in. So we can reset whenever we want. And what we're also going to do is we're going to remove this second input. What's happening right now is that these 100 points in our second input are basically being used to check for neighbors that are accessed here. And now, if we remove this, what's going to happen is our network is going to be checking just these points for neighbors to themselves. So, for example, if we have this point here, it's going to be looking for points that are in that neighborhood. let's reset that network and see what happens. And we can see we have this sort of more uniform grid-like option. Playing around with these functions as well, control some of this too. And let's also switch that math mix to have a stronger pull on the dir. And so much of this can come from thinking about like play with these max neighbor distances, how many neighbors we're checking for, giving us these sort of interesting effects. Different algorithms as well. Some of these have a much longer drain or will even crash the system. Okay, I hadn't saved and reset my system and just quickly rebuilt that network. And what we have here, just to recap, is we have our point generator going into a feedback. Our neighbor is set to inverse distance weighted average. And in the math mix, I'm getting the direction vector from that inverse average for each point. I'm then scaling that direction vector, and then I'm adding that to our P. And when I reset the system, it looks like this, where it pulls towards these certain points, which again is a super cool effect. Slowing that down more just gives us a slower pull. What you could go ahead and do is you could have some kind of noise added to the system, and rather than controlling the noise, we can turn off the combine operation on the output, and let's just say V speed, so that's going to control how fast our vector pushes and pulls, and we'll turn this down a bit, 0.01. Now add in V speed here. And then we can animate this. And then again, we get a sort of an interesting effect here because the V speed where we're pulling or pushing isn't standard across the board. If we actually went ahead and moved our noise up in this offset just to make sure it generally is positive, then things would still pull towards each other, just at highly different rates. And again, we can pull that down. Or you could go in here and you could just make sure that your V speed is absolute. So we go abs, V speed. And again, like I said, this is just sort of improvisational, just to show you different techniques that you could do with this tool. If I plug this into a trail, I can get some really nice effects. Link the trail to the keyboard in. And you get these sort of pull and push effects. Again, if we wanted something to pull to a specific point or set of points, we could use this second input. I'll just have 100, or actually 10, just so we can really see that. And again, we get these interesting effects. In the neighbor pop, controlling things like the scale of that neighbor's distance can do some interesting things, and also controlling this max number of neighbors. You can go really high with this. That's going to slow down your frame rate quite a bit, but you can play around with this to sort of get different types of effect as you move towards these particles. Something I like to do at a stage like this is start adding in operators to see what happens. First off, I'm just going to turn down my V speed. So I'll do like 0.1 just so things happen a little more slowly. And what I also want to happen is maybe have some kind of repulsion when it gets to a certain point. I just want to do a quick experiment here. I'm going to drag in my point easing tool. And this is something that's available on my Patreon, where basically it's a GLSL tool that creates easing between points in systems. And essentially what's going to happen is it's going to look for points that are close together and push them apart. Here we can see that that's really going quite strong. We have a really big radius, so I'm going to turn that down. We have a big strength, I'll turn that down, and I'll turn down my step to 0.05. But then we can see that we get a sort of flocking pattern happening here, where things pull together into certain areas, matching these points. And then they kind of cluster and they can't quite get as close as they'd like. You can set up different attraction weights here as well. You could also even set up something that's going to pull them even closer together and then kind of cluster in one spot. I'll just go like 0.05 across the board, and now we have this sort of nice pattern of things that are flocking together in their areas, and it almost creates a sort of volumetric flocking. If I add in a noise here and animate it and turn up this amplitude to say 1 and actually slow down that noise animation quite a bit, we should have flocks that are moving with their corresponding areas. And this is again an effect I really, really like. If you wanted to do something like use the neighbor in a sort of a post-production-y sense to delete some points, we could also add that in. I'm going to add in a null just after my trail. I'll add in a delete. And I'm going to use another neighbor right here. And pause for the time being, because what I want to do is I want to add in that set of displaced points. And again, what I'll do is I'll use my distance attribute distance. And then what we can see is we have our orb that sort of centers around that section that is now visible. We could invert that, and then we could put maybe like a sphere or something that's going to match that space, and that's going to be at the front of these sort of tendrils. Let's try that real quick. And we'll say the sphere size is going to be 0.1. Copy. Drag over that. And now we have this sort of effect that looks like almost squids moving through space that have these tentacles following them. As I mentioned at the beginning of this video, this was more of an experimental improvisation with the neighbor pop and some other tools that kind of feed into that. And I hope this has been useful to watch. What I'm going to do is make the examples from today available in my Patreon. The first few examples that we looked at will be available for all tiers, and this more advanced example will be available for component tier. I'm also going to do a separate video for component level subscribers that goes more in depth on this effect, where we create a sort of push-pull flocking, and how we can use that neighbor grouping in space to add color to these flocks to create a more unique aspect for each of these individual flocking organisms. Thanks for watching, and see you next time.